All right, so in this video, we're going to talk about, why are we even finding the limit of, applying the summation formulas and, applying all that algebra. Well, really, it's to find the area under a curve. And this is another calculus topic that you will explore in depth in AB should you choose to take it. So remember I said, part of calculus is finding derivatives or finding rates of change, right, with the slope equation, the slope of the tangent line, right, or slope at a specific point. The other part of calculus involves just finding area underneath the curve. And we're just really going to, do the basics of just calculating area. Later on, when you guys enroll in calculus, you'll, learn a bunch of formulas to help you calculate, area under a curve. All right, so I have two pictures here, roughly drawn, of the same curve. And if I were to ask you to find the area underneath this curve, I only have four rectangles over here, right? Not drawn with a specific, order. Some of these rectangles are above the curve, some of them are below it. But the point is, as you can see, that as I increase the number of rectangles, right, from four to I don't know how many I drew over here, you get a better approximation. Okay, so better approximation as I increase the number of rectangles, better approximation of the area, right, underneath the curve, right? If I only have four rectangles, right, it's not going to be that great. So if I increase the number of rectangles, you can hopefully see it'll give you a better approximation of the area. Okay, so I'm sure there's computer models that will help you do this much better than me drawing it by hand, but that's the idea. All right, so now we are tasked to actually find the area under the curve. And in order to do that, we need some kind of generic formula. And so what is this formula that we can come up with? Well, on this interval right here, why don't we label this guy right here A? This is my left-hand interval. And we'll call this guy right here my B. This is my right-hand interval. And so if you remember the area of a single rectangle, right? Well, it's just base times height, right? Or width times height. I'll just call it width times the height. Right? That's their area formula of a single rectangle. So again, I want to apply a formula. So how do I calculate, assuming that these rectangles are equal width? So we'll say assume equal width. What I can do is do right minus left, right? I can write the width of a single rectangle, right, is B minus A, right minus left, divided by the number of rectangles. In this case, I have four, right? And that would be the width of a single rectangle, right? So let's say this is 8, this is 0. 8 minus 0 divided by 4, the width would just be 2 for each one, right? So instead of calling it 4 rectangles, right, we'll just call it n. N is the number of rectangles. Okay, so calculating the width, hopefully you can see it's right minus left divided by the number of rectangles. This is the width of a single rectangle. Okay, well, we haven't got very far. All we've gotten so far is the width, right? But we also need to figure out a formula for the height. Now, how do I figure out a formula for the height? Well, the way you calculate the height, right, is basically where this rectangle meets the curve, right? So whatever this x value is, I just plug it into the function. It's going to meet the curve right there. That will give me the height. And, if I plug it into here, that will give me the height, right? If I plug it into here, that will give me the height. In fact, I probably drew this rectangle a little bit wrong, just not to confuse you, overly confuse you. Let's draw this a little bit better so it'll make my point a little bit more clear. Okay. There we go. Okay, so basically, if I know whatever this x value is, I could just plug it into the function. That will give me the height of this rectangle. If I know what this x value is, I'll plug it into the function. That'll give me the height of this rectangle, and so forth, right? If I know this x value, I know this, just plug it into the function. That'll give me the height. If I know this x value, which I do, right, I'll plug it into the function. So how do I write that? Well, you already know that the width of a single rectangle is b minus a over n, right? So if I ask you, what is this x value, right? If I use, hey, this is 8, this is 0, 8 minus 0, divide by 4, that's 2. If I ask you, what is this x coordinate, you would say 0 plus 2, which is 2. If I say, what's this coordinate, you would say 2 plus 2, which is 4, and 6. Well, it's the same concept. Instead of saying 0 plus 2, I'm going to say a plus, this x value right here is a plus b minus a over n. Okay, so again, without any numbers, that's that x value, right? And if I ask you, what is this x value? Well, I just take this term and add a plus b minus a over n, right? So I would add another b minus a over n, right? This would be a plus 2 times b minus a over n, right? And so forth. This would be a plus 3 times b minus a over n. Okay, so that's really the x values. And basically the right side of this guy right here keeps increasing by b minus a over n, right? This would be a plus 3 plus b minus a over n. Okay, so how would I come up with an expression for the height then? The height is, right, if this is the x value right here, the y value is f of a plus b minus a over n, right? If I say, hey, what's the height over here? You would say f of, a plus b minus a over n times 2, right? Because, I just take this term and add b minus a over n. All right, so the height in general would be f of parentheses a plus b minus a over n, right? This would just be for the first term, but basically this term here on the right just keeps increasing, and if it keeps increasing, we'll just make it into a counter. We'll call it I, and that will be the height. Okay, so I is your counter, and so hopefully you can kind of see that algebraically why the height is f of a plus b minus a over n. Okay, all right, now we still have not come up with a formula, but we're very, very close. We have the width of a single rectangle. We have the height of one rectangle, depending on what your counter is, right? Let's say I is 0, right? You would just plug in f of a, right? If I is 1, right, you would plug in f of a plus b minus a over n. Let's come up with a generic formula now. I know that the height of a single rectangle is f of a plus b minus a over n times I. Okay, a plus b minus a over n times I. This is my height. And I know the width is just b minus a over n. Okay, so that is a single width. That's the width, I should say, the width of a single rectangle, okay? All right, so the area of a plane region, let f be continuous. Continuous just means, remember, it's a smooth curve, okay? So if you lift up your pencil, it's no longer continuous. Non-negative on the interval from a to b, inclusive. The area bounded by the x-axis, x is equal to a, x is equal to b, is given by this. Area is equal to height times width. But I'm still not done, right? This is just the area of a single rectangle, right? But I want to add all these rectangles. And the fact that, incorporate this knowledge, that the more rectangles I have, the better approximation of the area underneath the curve, right? So if this is the area of a single rectangle, and I have a counter, I'm definitely going to have a summation symbol, right? Because I have to add all the rectangles from I is equal to 1 to n, right? And I'm going to include the fact that because the more rectangles I have, the better approximation I have underneath the curve, I'm going to add a limit symbol, the limit as n goes to infinity. Okay, so that is the area formula for the rectangle, using rectangles. And hopefully you can kind of see where this formula comes from, and it's quite important, right? Otherwise, if you just see this, you're like, what does this actually mean? And oftentimes when you take calculus, the actual computations and derivatives of integrals are not super difficult. You have to be able to understand the concepts. You have to know where the formula comes from. Okay. Sometimes, like those formulas for the summation problems I did in the previous video, those ones you just memorize, but this one's important to know where the formula comes from. Okay. All right. So I'm going to move on to the example in this next section here by just, not actually using the formula, but just, kind of using our brains here, using some algebra here. It says approximate the area of the region using the indicated number of rectangles of equal width. Okay, so I have this function right here. It's a parabola, right? 1 minus x squared. And the indicated number of rectangles in this picture right here is just 4. And I believe on your homework, you can just count the number of rectangles if they don't tell you. But on problems 21 and 22, they actually tell you the number of rectangles. So just, kind of follow along. All right, so we're going to use these 4 rectangles, and we're just going to calculate the area under the curve based on this function. All right, so the first thing I'm going to do, right, is just calculate the width of a single rectangle, right? The width of one rectangle, right? I mean, you could do a couple things, right? You could just say, hey, from here to here is 1/2. But I'm just going to do right minus left, 1 minus -1, right? Just do b minus a divided by the number of rectangles, which is 4. And the width of a single rectangle, of course, you can see is 1/2. Okay. Now, the height of each rectangle, right, that's underneath this curve is dependent on where the rectangle is drawn and where it's located underneath the curve, right, where it intersects the curve. So if I want to find the height right here, right, I would plug in f of, -1/2, right? And so what I'm going to do is now just, come up with the area formula. Area is the width, right? This is my width. And then times the individual heights at these points. So whatever this value is, we'll say f of -1/2, right? Why are you plugging -1/2? Because that's the height for this first rectangle. So that's for rectangle number 1. And then plug in f of 0. Well, why is f of 0? Because that's the height of the second rectangle, right? Plus f of 1/2. And then plus f of 1. Okay, so this is poorly drawn, but that point, this rectangle does intersect that curve. So f of 1. Okay, so what do these represent? The height of the first rectangle, height of the second rectangle, height of the third rectangle, height of the fourth rectangle. And you can multiply the widths individually, but you can just pull out the 1/2 like I did over here. All right, so hopefully that makes sense, right? And the last part is, of course, just to evaluate. Looks like we could do this in our head. This is 1 minus 1/4, which is 3/4. F of 0, you can just see from the curve, right? That's just 1. F of 1/2, 1 minus 1/4, again, is 3/4. And then f of 1 over here. Okay, so f of 1 technically is just 0, right? So actually I drew this picture a little bit poorly. We'll just say this last rectangle will be right here. Okay, so almost, because I kind of made this problem up. The height of that last rectangle, we'll just say it's at 0, okay? All right, so you can simplify this. Let's see, you're gonna have 6/4 plus 4/4, which is 10/4. And you're going to get a 1 over here, you're going to have 5. Okay, so you're going to have 5/4. So make sure you write your units. We'll call it 5/4 units squared. Okay, so a little bit of a typo, right? Because f of 1 clearly is going to be 0, so this rectangle has to be drawn right here. Okay, so this one I didn't really use the formula. because I actually had the numbers, and you know, that's kind of the idea of, you know, calculating area under the curve.